In 5G network, every microsecond counts. Imagine hundreds of smartphones and IoT devices transmitting data at once. If the signal don't reach the base station in perfect sync, chaos begins. That's where timing advance and synchronization come in. The invisible mechanisms keeping every transmission precisely aligned. In this episode, we'll explore how 5G ensures every device, near or far, stays perfectly timed, delivering the speed, reliability, and harmony that define next-generation connectivity. In a cellular network, timing isn't just about precision, it's about harmony. When hundreds of user devices transmit simultaneously, their signals must arrive at the base station perfectly aligned. Even microseconds of delay can cause symbol overlap and severe inter-symbol interference. That's where timing advance comes in, a mechanism ensuring uplink signals from all UEs reach the base station in sync, regardless of distance. Alongside this, synchronization procedures keep both network and the user equipment time-aligned for seamless communication. In 5G new radio, the timing advance uses a final base time unit, TC. Each step equals to 16 TC or about 8 nanoseconds. This means a UE can fine-tune its transmit timing with sub-nanoseconds precision, keeping all uplink signals tightly aligned at the G node B. The network continuously measures the UE signals arrive and sends TA commands whenever it detects drift. Synchronization in 5G operates on two layers: network synchronization and UE synchronization. Network synchronization ensures all G node B in a region share a common time reference. This is essential for features like TDD, carrier aggregation, and comp, where timing consistency prevents interference. UE synchronization ensures that each device aligns both frequency and phase with its serving cell before data transmission. It starts with primary and secondary synchronization signals and fine-tunes through reg, preamble, and TA commands. Compared to LTE, 5G new radio enhances timing and synchronization through several mechanisms. Higher resolution TA steps allow finer uplink alignment, multi-cell timing management, enabling smoother handover across beams or cells, GNSS and PDP-based G node B synchronization, reducing drift between cells, dynamic TDD coordination, ensuring uplink and downlink switching remains interference-free. These improvements are crucial, especially for millimeter wave and URLLC applications. With TC-based granularity, 5G can align uplink bursts from multiple UEs to within just a few meters, an essential capability for wider bandwidths and TDD operation. During the reg procedure, UEs transmit a preamble. The G node B measures its timing offset and responds with a random access response. That includes the timing advance command. This allows the UE to immediately align its uplink transmission timing. Later fine-tuning continues through uplink control signaling whenever the network detects drift. Let's visualize the harmony. Imagine hundreds of UEs, each transmitting precisely timed uplink bursts, perfectly synchronized in frequency, time, and phase. The base station receives a clean, interference-free uplink, enabling high throughput and reliable connectivity. That's the power of timing advance and synchronization in 5G new radio. To summarize, timing advance aligns uplink transmissions from all UEs. Synchronization ensures both UE and network timing coherence. 5G enhances timing precision with final steps, GNSS, and PDP sync, and dynamic coordination. Together, they enable 5G's high capacity, low latency performance. In our next episode, we'll explore episode 9, power class and transmitter characteristics. That's all for today. If you like this video, please subscribe, share, and like. Thank you.